And I think we're live. All right, welcome everyone to the RPSP online seminar series. Let me make sure that I closed all the YouTube. All right, so we're good to go. Today's seminar is dedicated to one of the NASA drive centers, the Center for Geospace Storms, which has been recently selected for the Phase 2 award, which is a big deal for the for us is the inner magnetospheric community because of the large scope and interinstitutional nature of the drive centers. And I'm very grateful to the PI, Slava Merkin, and his colleagues who graciously accepted my invitation and are going to give us a broad overview of the center, considering how relevant the scope or science scope of the center is to understanding energetic particle processes in the near Earth space. With that, I'll just give the floor to our first speaker, Slava Merkin.
Yes, hi everybody. I'm happy to be here. Thank you very much, Sasha, for the invitation. I'm going to start sharing my screen now. Hope you see the right slide, the title slide.
Yes.
Okay. All right. So when we were invited to give this talk, we decided to do something different this time. Instead of me talking for the whole hour about the work that other people did, I thought I would start by just giving you folks a quick introduction to CGS and then give the floor to the rest of the folks here who are, most of them are early career scientists, and they're the real driver behind everything that we do here. So let me just start quickly by introducing the project. So as you can see there, the vision of our center is to transform the understanding of predictability of space weather. It's a large collaboration. You see on the bottom there the organizations that are involved. We're very happy that one of our co-Is, Roger Varney, is moving to UCLA and will be starting a faculty position there. So UCLA will be joining our family in Phase 2. As part of the proposal, we were asked to formulate not only a vision statement, but also a mission statement. So our mission statement, in short, is innovate, empower, and discover. And if I were to expand on that, that's what you see on the screen. We strive to innovate space weather modeling, empower the stakeholder communities, including scientific, academic, operational, as well as the broader public. And then together with these empowered communities, discover how storm time geospace responds to solar disturbances. So the fundamental motivation for this work is the realization that we're dealing with a system that is highly complex, multi-scale and multi-physics. I'm talking about geospace, and it is this complexity that underlines the challenge of space weather prediction. We highlighted 3 specific challenges that we are dealing with. Number 1, the cross-scale interactions between the different domains of geospace require treating it as a whole. At the same time, in the past a few years, we've realized as a community the importance of mesoscales. So the models that we develop need to resolve mesoscales in all of the relevant domains, and these mesoscales mean different things in the different domains. And you see some of them highlighted on the slide, and hopefully the movie is playing as well. And finally, another relatively recent realization is that to understand the effects of space weather on the ionosphere thermosphere system, we need to include coupling not only from above with the magnetosphere, but also from below with the lower atmosphere. So what do we do to address these challenges? We build this new model, which we call the multi-scale atmosphere geospace environment, or MAGE model. And what you see here on the slide is a picture that really just tries to highlight the enormity of the scale separation that we're dealing with. Mesoscales in the magnetosphere, for example, are represented by these bursty bulk flows. And at the inner edge of this system, you see just a thin foil of the atmosphere and ionosphere. But if you zoom in on that, you see that it's a world unto itself with its own complexity and multi-scale interactions and so forth. And so we're building this model that includes all of these regions, but at the same time resolves all of the relevant processes. On the right here, you see basically a statement that we're trying to resolve all of the challenges that I mentioned. I probably don't have time to go into the details of the model, and you'll see some of the highlights in the following presentations by the other folks. So far in phase one, we have coupled our global magnetosphere model with the ring current model and with the ionosphere thermosphere model. In phase two, we will expand it to include all of these different models and regions. I want to highlight that we're doing it at a very high resolution in all of the involved domains, and this resolution is important to capture the processes that we think are important, such as bursty bulk flows in the magnetosphere, or tongues of ionization and polar cap patches in the ionosphere, or gravity waves, or some fraction of the spectrum of the gravity waves in the lower atmosphere. And we are working hard on making this model available at the CCMC, and we're also planning to release it under an open source license in phase two. So we have three key science themes, which I will describe only very briefly. You're welcome to go to our website and see the science themes in more detail, including the specific science questions. But at a very high level, they can be described as the first theme is the multi-scale ring current buildup. The second theme is the mesoscale ionospheric structure. And the last one is the lower, not last but not least, the lower atmosphere ionosphere coupling. Before I give the floor to Kareem, I'll just make one critical point, which is we want to redefine what we mean by validation in our field. We want to go after model validation, as in, does the model do the right physics? Does it capture the right processes, as opposed to trying to compare every single wiggle to between the model and observation. And also we want to explore more rigorous uncertainty quantification. I will give two examples of these, what we call science metrics, or going after processes. One is storm time BBFs, bursty bulk flows in the magnetotail. This is from Shinotani's work, Otani and Mukai. And essentially it says that statistically during storm time, the electric field is elevated in the magnetotail during the main phase, but it's not due to the velocity of the flow, it's due to the magnetic field. And the other science metric that we are exploring is the so-called downside current wedge, which again, Shinotani has discovered in the last few years. And I'm gonna stop here and transition to Kareem, who is going to talk to you about this storm time current wedge in detail, to the extent that it's possible to do in 10 minutes. Okay, Kareem, go ahead.
Right, thank you, Slava. Some level of detail, let's say. Could you go to the next slide, please? And the one after that. Thanks. So yeah, I just wanted to add a little bit to what Slava was talking about in terms of how we want to think about validation, and this is done in the context of storm time validation and what Slava mentioned, the downside current wedge. So we know that during storm time we see depression of the ground magnetic field at low latitudes, and we also know that we often see a large amount of MLT asymmetry, with a depression at dusk being larger than the depression at dawn. This has traditionally been interpreted in the context of the partial ring current model, which I'm showing us sort of schematically in the top right, in which case we have MLT truncation of the ring current and current closure through the dusk side eastward flowing electrojet. And so this picture has an implication that there should be a correlation between dawn-dusk asymmetry at low latitudes and auroral activity on the dusk side at high latitudes. And this prediction was tested by Shinotani in a paper recently using statistics taken from hundreds of storm main phases. And what he found was that there wasn't actually a correlation between the dawn-dusk asymmetry and the enhancement of the dusk side electrojet. In fact, there was an enhancement of the dawn side electrojet correlated with the dawn-dusk asymmetry. And so this leads to this different picture of a dawn side current wedge, which I'm showing here on the bottom right, in which case we have sort of a larger MLT extent of the ring current and current closure through the dawn side electrojet. So this is a robust correlation that comes out of hundreds of sort of mining statistics from hundreds of storms. And so as a modeler, an immediate thing I want to ask, of course, is, do I see that in my model? And if so, what can we learn about it? Obviously, it's always impressive to me how much people can learn from ground data, but it would be, great if we can actually then use models to put a much better sort of contextual picture to sort of how the magnetosphere connects to the ionosphere in creating the sort of behavior that we see on the ground. And so this is the sort of study we wanted to look at. So we're using here the March 2013 storm as a case study where there was a lot of observed dawn-dusk asymmetry, and this is a storm that we've looked at several times in the past. So let's see what happened. Could you go to the next slide? And so the first question is, do we see the same correlation in our model that we do, that Shin did in the supermag data? And this would be sort of a weird buildup if the answer was no. And the answer is, of course, yes. Here what I'm showing on the top right, this is showing the dawn-dusk asymmetry as the black curve, which is essentially the dusk side depression minus the dawn side. And you can see that we see these two spikes in dawn-dusk asymmetry at about 10:30 and 11:30. And then what I'm showing in blue and red is the auroral indices. This is showing the SMU and the SML. Blue is the SMU, which we can think of as a proxy for the dusk side electrojet. And red is the SML, which we can think of as a proxy for the dawn side electrojet. And just looking at this, we can see that there's not much correlation between the blue line and the black line, but we are seeing a significant amount of correlation between the red line, the dawn side electrojet, and the black line, the dawn-dusk asymmetry, at both periods where we see this, strong asymmetry at 10:30 and 11:30. So the point here is we do see the same effect, the same correlation between this asymmetry and the enhancement of the dawn side electrojet. Now let me show a little bit from this, the actual simulation itself. Here what I'm showing, let me focus on the sort of bottom left panel. This is a slice taken in the equator. It's showing the non-dipolar component of the magnetic field. So red means stronger than dipole, black means weaker. And remember, we see the asymmetry at about 10:30 coming up now, where we see this strong dawn side activity, BBFs penetrating inside of Geo, and then we see it again here at 11:30, which again, we get strong dawn side activity, BBFs on the dawn side penetrating inside of geosynchronous. So that's great. I love mesoscales, I love BBFs. What can we learn about this? So go to the next slide, please. Thanks. So, what can we learn about sort of currents coming from the magnetosphere going to the ionosphere and so on? Here I'm showing on the top left, this is showing in the ionosphere, basically the x-axis is time and the y-axis is MLT, with dawn towards the bottom of each panel and dusk towards the top of each panel. And so what I'm doing in the ionosphere is essentially at each longitude, at each MLT, I integrate over all latitudes the field-aligned current on open lines, which is the top panel, then the field-aligned current on closed field lines, which is the middle panel, and then the Hall current, which is the bottom panel. And in this color scheme, basically red corresponds to eastward flowing Hall current, green corresponds to westward flowing Hall current. So let's start by just orienting ourselves. If we look early on, basically towards the left of that panel at 9.5 hours or so, The top panel, the open field lines, we see what we think of as a sort of typical R1 current system. In the middle panel, we see what we think of as a pretty typical R2 current system. And on the bottom panel, we see on the dusk side towards the top, red, which means we have a dusk side electrojet, and sort of towards the bottom on the dawn side, we see sort of like green, meaning we have a sort of weak dawn side electrojet as well. So now if we go to when we see the asymmetry at 10.5 and 11.5, you can see that in both cases, what we're getting in the closed field line region on the dawn side are these up-down currents, sort of these R1 sense wedgelets, which is sort of expected because we see these BBFs penetrating inside of geosynchronous on the dawn side. And you can also see just how clearly these strong enhancements of the dawn side electrojet, the sort of darker green, corresponds to those up-down currents and where they occur. And in particular, we see sort of this multi-scale structure in the enhancement, where we have a fairly broad enhancement of the electrojet over the full sort of dawn quadrant, but there's also sort of these very clear local striations that are matching these up-down currents. And so what we're seeing here is that these sort of BBFs on the dawn side are really connected to these enhancement in the dawn side electrojet. What I'm showing here is just a little bit more sort of in the animation. This is showing on the right, this is showing the arrows are the equatorial currents in the magnetosphere, so largely the ring current and the tail current. And then these three dials in the center are basically just the same thing I'm showing here on the left. The outermost dial is the open field line currents as a function of MLT, closed field line currents, and the Hall current. And so if we watch this, we can see that as you go towards 1030, we get these dawn side BBFs and this propagating eastward enhancement in the dawn side electrojet. And we see that we're getting these feeder currents coming from sort of pre-noon, post-dawn, sort of brunch region, driving that enhancement in the dawn side electrojet. And so leave it here for now, but just make the point now that we see this dawn side current wedge associated with dawn side BBFs. Those dawn side BBFs are going to bring dipolarizing flux into the inner magnetosphere. They're going to bring energetic ions, which leads to pressure and changes in the field line currents in the R2 system. They're also going to bring energetic electrons that lead to diffuse precipitation and this eastward propagating conductance enhancement. And in particular, sort of the role of ions and pressure and field line currents and electrons and precipitation and conductance will lead to important structures in the actual flows in the ionosphere as well. And with that, let me hand it to my friend Dong.
Hello. Slava, you go to the next slide. Hello.
We can hear you well.
We can hear you.
I mean, I'm still seeing Kareem's slide.
Slava, can you go to the next one? Or is it giving a problem?
Yeah, sorry, I was looking for the unmute button. Let me reshare because I was moving the slides.
Okay.
Can you see it now?
Yes.
Okay.
Okay. Yeah. Hi, everyone. And thank you, Kareem. What you just talked about is also a good scene setting for me. The dawns here are just not quiet. So yeah, here I'm sharing our recent work on the dawn side subaurora polarization streams, or SAPs, trying to provide an additional perspective about how the dawn side geospace responds during storm time. So for the past decades, when people talk about the SAPs, they are uniquely referring to the westward plasma flow in the dusk side to midnight sectors. It's actually not until a few months ago that a similar structure on the dawn side was identified. So basically, I'm referring to the enhanced eastward plasma flow on the dawn side below the aurora boundary. So here we use a major model trying to understand the driving mechanisms of the dawn side SAPs. So here, this event, excuse me, occurred on November 20th, 2003. It was a superstorm with a DSD minimum of about -500 nanotesla. So as you can see in the top row, which shows the zonal ion drift in the northern ionosphere, The Dawn-side saps basically is on the top right, the red belt between the magenta and the green curves. The Dawn-side saps just looks so similar to the classic dusk saps. Basically, is featured by this very narrow flow channel, and it's between the region 2 Phelan current boundary, shown by that green curve, and the equator with the aurora boundary. And as you know, below the aurora boundary, the conductance was relatively low. So as required by the current closure, there has to be an enhanced equator E field, which drives the eastward flow. So this is just the classic scenario to explain the generation of saps. You can just switch the direction of the E field and the Phelan current direction to explain the similar case on the dusk side. However, there's a difference between the dawn side and the dusk side saps as shown on this plot. So you can see the dusk side saps occurred as early as 6 UT in this case, which was actually before the commencement of the storm. But the dawn side actually didn't show up until a few hours later. So in the bottom, also Slava, could you play the 2 videos? Thank you. Yeah, so again, the formation of both the dawn and the dusk side sap have to do with the intensification of the region 2 Phelan current, which has to extend below the aurora boundary. And as we know, the region 2 Phelan current is mostly contributed by the azimuthal pressure gradient of the ring current. And it's just like shown on this test particle simulation with the chimp model, the ring current ions can effectively get to the dusk side at 6 UT and build up the ring current pressure there so as to intensify the region 2 Phelan current that creates the saps. However, in the second case, during the main phase of a storm, they can effectively get to both the dawn side and the dusk side. So that creates the necessary condition for the formation of the dawn side saps. Could you go to the next slide, please? So next, we try to understand the different behaviors of the energetic ions from a more fundamental perspective. Excuse me. So as we know, during the transport of the energetic ions from the plasma sheet to the inner magnetosphere, they can be very well described by the adiabatic convection drift. Basically, this means when an ion is transported toward the inner magnetosphere, it can be described with the energy invariant. Basically, that's a combination of its kinetic energy and the flux tube volume. So as it gets closer to the Earth, the kinetic energy would increase because of the flux tube volume increases. So as a result, the E cross B drift and the magnetic drift, including both the curvature and the gradient drifts, which is energy dependent, would have a switch from E cross B drift dominant at a larger air share to the B drift dominant at a smaller air share. So basically, that's where the transition from yellow to purple occurs. And during the main phase, when the convection E field, convection electric field is so strong, this transition just occurs at a much smaller air share. So that means most of the, so that means a lot of the ions can effectively get to the dawn side before they have to drift westward because of the magnetic drift at a very small air share. So this is like a quantitative transition. A quantitative change leads to a qualitative changes. So basically, during this kind of superstorm, the energetic ions can build up on the dawn side only when the convection is so strong. So in that regard, we suggested the dawn side saps as a feature of major geomagnetic storms. Could you go to the next slide, please? So I used to show this slide first in my previous presentation, but here, just to make sure a transition from Kareem's and also to the next part by Shanshan. So one of the critical factor that we can simulate SAPs and resolving its fine structure is because in this major model, we have adopted a combined precipitation. So basically, that means we are using the MHD parameters from the Gamera model to derive the monogenetic electron precipitation, as you can see from the top left, shown by the red arrow. That's associated with the upward region 1 Phelan current. And also, we derive the diffuse electron precipitation from the kinetic-based RCM model. And with this kind of physically more comprehensive description of the auroral precipitation, we can more reliably resolve the tiny difference between the region 2 Phelan current and the auroral boundary, so that we can resolve the SAPs, including the mesoscale structure of the flow channel. And what's more exciting about this precipitation model is that we can go further by including more wave features and wave particle interaction dynamics when deriving the diffuse precipitation. That's what Shanshan is going to elaborate in the next part. So I'm stopping here and hand it to Shanshan. Thank you.
Thank you, Don. And Shanshan, you're up.
Hi, everyone. Can you hear me right?
Yes.
Hi, as Kareem and Don has just mentioned, the electron precipitation plays a very important role in the MIT coupling and may affect many mesoscale processes such as SAPs during the storm time. In the MAGE model, the Rice convection model tracks the inner magnetosphere protons and the electrons in different energy channels and provide diffuse precipitation in the MIT coupling. RCM assumes the charged particles have isotropic pitch angles, and for a very long time, a diffuse precipitation model called the Fudge model is applied. The electron lifetime for energy channel K is approximately the total plasma content inside the flux tube eta K divided by L, which is the loss electron number flux per unit magnetic flux. The electron lifetime can be written as a function of energy invariant IK, the ionospheric magnetic field strength BI, and the flux tube volume V. A Fudge factor of 1/3 is used to measure the deviation from the state of strong pitch angle scattering. The electron precipitation number flux and energy flux can be derived based on the exponential decay of the flux tube content. However, the same Fudge factor has been applied to the electron loss and of all the electron channels, and it is irrelevant to the local wave modes and the geospace condition. Could you click, please? Yeah. So in order to capture the implication of the wave particle interaction in the electron loss, we implement a Greybox approach to improve the diffuse electron precipitation modeling. A Greybox model combines the knowledge of the physical phenomena and the statistical information. Another click. Here, MAGE model serves as a first principle white box model, and another click. And the wave particle interaction induced electron loss is a missing piece in the physics of RCM, and we need data-based wave dependent electron loss model to serve as a black box. Next slide, please. Currently, we have incorporated Corals wave and Heath wave in the electron loss. The Corals wave model is provided by our collaborator, Dr. Dedong Wang at GFZ Helmholtz Center, Potsdam. He uses a quasi-linear approach to turn 5 years of RBSP data into an electron lifetime model. Sensitivity study shows the electron outside the loss cone with different pitch angles have similar electron loss rate. This means the derived electron lifetime is independent to the pitch angle distribution. And we can immediately use the electron lifetime as model input to the RCM. For the heat wave, we use a Olova model published in their 2016 paper. Both Chorus and heat wave models use KP, MLT, L shell, and electron energy in the parameter space. Each dimension has certain range and grid resolution. Here, the right figure is an example of spatial distribution of electron lifetime for electron with 10 keV energy at Kp equals to 3. We have developed a particle loss module inside RCM to interpolate into the parameter space and extract electron lifetime based on the local particle energy, the spatial location, and the geomagnetic activity level. Next slide, please. Yeah. The Greybox model is tested in the simulation of 2013 St. Patrick's storm, and it is compared with the Fudge model run. The top panel shows the equatorial plane view of the electron lifetime distribution for one of the RCM electron channels. The two black contour lines shows the plasmaspheric density at 10 per cc and 100 per cc. The right panel shows the color-coded wave model type that have been triggered. The bottom panel is ionospheric view of the total electron energy flux based on the loss model. So in general, the Fudge model produces much shorter electron lifetime than the Greybox model. Inside the plasmasphere, where the cold plasma density is larger than 100 per cc, heat wave is triggered. Outside the plasmasphere, density is smaller than 10 per cc, the Chorus wave is triggered. And you can see at the plume region, a hybrid mode of both wave is triggered. Since the Chorus wave model covers the region within 7 Earth radii, outside the L shell equals to 7, we use a strong scattering loss model in the plasma sheet. Next slide, please. So the top panel on the left figure shows a DMSP measurement of the electron differential number flux in the color contour and the total energy flux in the black curve. The local electron lifetime versus the local electron energy of all the electron channels is plotted in the red curve. And we can clearly see the selection of the precipitating electron by the wave models. The low energy electrons can resonate with the local wave modes and get cannot resonate with local wave modes and get little chance to precipitate, get lost in the loss cone. And however, with for the electron with energy that is too high, say larger than 100 keV, it could deviate from the resonant energy and it can stay longer in the magnetic flux tube. The Fudge model does not have such selection effect, and the electron lifetime decreases as the electron energy increases. So in the spectrum, we can see the Fudge model overestimate the high energy population, which is marked by the red box. Whereas the wave model is able to suppress the high energy population, and it gives a better estimation of the energy distribution as well as the total energy flux. On the right, it is a snapshot taken at the at 8:34 UT, where the satellite is at the center of the precipitation flux near 18 MLT. The equatorial plane view of the electron lifetime is mapped to the ionospheric in the middle panels. The red color in the center stands for open field line region, so we assign a huge number to it. Around 18 MLT, we can see a narrow band of short electron lifetime in the Greybox model, and it corresponds to the brightness of the precipitation energy flux in the bottom panel. We can see the energy flux distribution has strong dependence with MLT, and the precipitation at the plasmaspheric plume region is suppressed. So in summary, the controlled experiments demonstrate clear modulation by the wave models in the energy and the spatial distribution of the diffuse electron precipitation. So for future work, we will incorporate other wave models in the particle laws, such as EMIC wave and the ECH wave, and we call for collaborations in the data-driven wave model application inside MAGE. And that's it. Let me hand it over to Adam with his work of test particle modeling of radiation belt. Thank you.
Thank you very much, Shanshan. And Adam, you're next.
Thanks, Slava. You could go to the next slide. So I wanted to talk about some of the work that we've been doing, kind of extending some of Shanshan's work that she showed, ingesting empirical wave models into our simulation to see how these waves impact the variability of the radiation belts. And the Van Allen probes have provided a wealth of information on the different individual mechanisms that control radiation belt variability. But since these mechanisms often occur simultaneously and over a range of spatial and temporal effects, it's remained a major challenge to try and identify the relative role that each mechanism has on the system driven during storms. So we've tried to take what we've learned from the Van Allen probe's mission and try and build a first principles model that can capture all of these critical features and allows us to isolate each individual mechanism. But in order to do this, we really need to be able to resolve large-scale features like the electromagnetic fields that these radiation belts are trapped in, as well as kinetic scales, as the way particle interactions can violate the first adiabatic invariant. So to try and do this, we are combining global MHD and test particle simulations, like you see the videos you see on the right-hand side. And you've already heard a really good description of our global MHD model, the MAGE model, from both Slava and Kareem and Dong and Shanshan. But what coupling test particle simulations with this MHD solution allows us to do is to accurately evolve our radiation belts through dynamic storm time electromagnetic fields. And it also allows us to capture injections that transport and accelerate plasma sheet electrons into the radiation belts during storm time dynamics, as well as magnetopause losses due to magnetopause shattering and Kelvin-Helmholtz waves that form on the flanks of the magnetopause, like you're seeing on the right-hand side. And since we are now capable of ingesting empirical wave models, we have gone ahead and what was once numerically extremely expensive, we are now implementing and incorporating wave particle interactions into our global test particle simulations here. And then ultimately the goal is to see how, to help us try to address some of these problems that we've had separating these acceleration and loss mechanisms, as well as help provide information on precipitating flux that potentially can feed back and affect the global fields, as Shanshan was showing for her diffuse precipitation. If you go to the next slide, please. So this slide is just quickly shows the marches through the methodology with which we are incorporating these local wave particle interactions into our test particle simulations. So first, I'd just like to highlight that we are evolving the electrons through simultaneously through the magnetic and electric fields provided by the MHD solution, as well as the wave spectrum provided by an empirical wave model. And for each time step, as we evolve the particles through the magnetic fields, we simultaneously calculate whether that electron for a given energy and pitch angle resonates with the local wave population. And if that particle does indeed resonate with the background wave population, we then go ahead and calculate a quasi-linear diffusion coefficient that was derived by Danny Summers in 2005. And this diffusion coefficient is local depending on the plasma conditions and wave conditions at the test particle. And it's an analytical expression which allows us to determine it for every single individual test resonant interaction. And once we have the diffusion coefficients, both in pitch angle and momentum and the cross diffusion term, we can calculate the resulting change in pitch angle and momentum by using a Fokker-Planck diffusion equation that's recast as a stochastic differential equation, which you see here in the middle of the slide, which corresponds to, or delta T is the resonance time. And here, this is the random walk term where eta alpha and eta p are random numbers generated from a random distribution. And these coefficients, A alpha, B alpha alpha, et cetera, are all functions of the diffusion coefficients that we calculated before. And these diffusion coefficients depend very strongly on the local wave spectrum and wave intensity, as well as the particle's pitch angle and energy, and the background magnetic field and plasma density. And since we are calculating these from an analytical expression, that allows us to, for each individual resonant interaction, to pull the background magnetic field and plasma density and wave characteristics and calculate those diffusion coefficients for that particle, and then select the corresponding diffusion coefficient based on the resonant wave. So what you're seeing on the top of this image is both the diffusion coefficients, the pitch angle, momentum, and cross diffusion terms at a particular point. Here, this is an L shell of 4.5 for a density of 20 particles per cubic centimeter for a wave amplitude of 100 picotesla. And this distribution is calculated every single wave interaction. And since this depends heavily on the background plasma, what you're seeing on the bottom right-hand panel is the ratio of the plasma frequency to the gyro frequency taken at a specific snapshot in our simulation, where you can see the plume of the plasma pods reaching out to the day side. And so this ratio will heavily impact both the strength and the amount of particles that will resonate for a given wave at a given time. So this allows us to be extremely dynamic in the simulation. If you go to the next slide, Slava. So before going on to the results, I wanted to quickly discuss how we're incorporating the waves into our simulation. Here we have incorporated resonance with parallel propagating lower band chorus waves, and I've been collaborating with Wen Li and Shanshan at Boston University to take their empirical wave model derived from Van Allen probes data, which provides us with the chorus amplitude, wave amplitude as a function of L shell MLT magnetic latitude. Additionally, the wave model is parameterized by the SML star. So for any given event, we can take the particle's three-dimensional location and the current SML index in the storm to determine the wave amplitude that is resonating with the wave. And since the plasma density not only affects the impact, the strength of the pitch angle scattering or energization that any electron will receive from the resonant interaction, it also strongly controls the wave location, as Shanshan was mentioning in her previous slides. So we can reparameterize the empirical wave model to be in according to the distance from the plasma pause and measure that plasma pause in our simulation the same way that they do in the empirical wave model, and then ingest those waves accordingly depending on the plasma solution in our simulation. So in order to understand the effect that these wave particle interactions have on the radiation belt dynamics, we decided to look at a case study extending Kareem's 2018 work, where he looked at the radiation belt intensity variation during the 2013 St. Patrick's Day storm. If you go to the next slide, please. So if you look at the video on the left-hand side, what this is showing is the intensity measured at the Van Allen probes, both A and B, in the top panel here and here, and the intensity extracted from a synthetic RBSP satellite from the simulation, both for the A and B here accordingly. And these are showing the intensity as a function of time on the left axis. Similarly, on the panel on the left shows contours of 1 MeV electron intensity shown in the equatorial plane and the corresponding location of the Van Allen probes at that specific time. And finally, DST throughout the event is shown in this bottom panel here. And there's a lot going on, and it's difficult to read the axes, but what you can see is that throughout the majority of the storm and all the main phases of the radiation belt model without wave particle interactions does a very good job qualitatively capturing all the features throughout all the phases. However, at MeV energies, you can see that the model is under predicting the intensity, which is expected since it doesn't include these wave particle interactions. So what you're seeing in the top right-hand panel is a slice across the Van Allen probe's A measurement at 3 MeV for a portion of the time in the recovery phase of the storm. And the RBSP intensity measurements are shown in black, while our simulations run with and without wave interactions are shown in green and orange accordingly. And you can see that just by incorporating wave particle interactions and resonance with lower band chorus waves that we can indeed account for some acceleration to these MeV particles as we would expect. And because we are using test particle simulations, we know exactly where our particles are at any given time. And consequently, we also know exactly when they leave the domain. So we can use these to study both the loss process, both through the magnetopause and through atmospheric precipitation. So what you see on the right-hand side is work led by Kevin Pham, where we've calculated the precipitating energy flux during this event that's caused by this increased wave particle interactions and pitch angle scattering just from these waves, so that we do not see without these processes included. So we are really excited to see going forward to be able to more quantify how these effects are affecting radiation belt dynamics and hopefully add more to the knowledge base that the Van Allen probes have already given us. Thanks.
Thank you, Adam. And this concludes our series of presentations, a potpourri, if you will, of this talk. So I'll just remind you what we've done here. I gave a brief introduction of the CGS as a whole. In conclusion of that introduction, I talked about our approaches for model validation, and following that, Kareem talked about this process that we're trying to reproduce in the simulation, which is the storm time dawn-side current wedge. Kareem passed it on to Dong, who talked about, again, a storm time phenomenon of dawn-side SAPs and the role of auroral precipitation and how we're modeling that. Shanshan then picked up from there and described how we use empirical or data-derived models of waves in the inner magnetosphere to inform our auroral precipitation modeling. And finally, Adam talked about higher energy particles, radiation belt particles, but also using data-derived wave models to inform wave particle interactions in the radiation belts. So that's the end of our talk. I'll just do a introduction for early career scientists and maybe for faculty members out there on the call. We will be hiring at the various institutions within CGS. Some ads will be out very shortly. Some ads will take maybe a couple of months to come out, but there will be postdoc positions and also graduate student positions with our faculty members. Okay, so I'll stop here. Thank you very much, everybody, and thank you very much, our CGS scientists, for these excellent presentations.
Yes, thank you, Slava, for putting it all together and coordinating it, giving a very succinct and at one hand and on the other hand comprehensive overview of CGS. Do we have time for discussion? We have time for questions. So it's open mic, raise your hand, or we have Jeffrey is first and then Robin.
So I was intrigued with the modeling of the SAPs, and I know you were looking specifically at dawn side SAPs, but as you all probably know, SAPs is one of the mechanisms that is hypothesized to be responsible for the very deep penetration of lower energy electrons all the way through the slot region. And I wonder, obviously you can look at that with this model suite, but has anyone looked at it? And is it a viable mechanism?
I don't know who best to take this question. So Dong has definitely looked at SAPs per se on the dusk side first and now at the dawn side. I don't think we've looked at specifically SAPs effects on radiation belt particles, but this will be.
I think it would require doing some particle tracing, but lower energy particles than, so not our typical radiation belt particles, but sort of tens and hundreds of keV, and looking not just at how deeply do they penetrate, but is it really the SAPs electric fields that are allowing them to overcome kind of standard convection? So I think that would be a fascinating thing. When and if you folks ever have time, let's talk about it.
Thanks. Great thought. Thank you.
Robin?
Yeah, just a quick question for Adam. In I think your very last slide, you had a little map of the precipitating flux. And I was just wondering how you define the loss cone. I mean, the inner boundary for the model is at 1 or 2 RE. So do you just set a L-dependent pitch angle for that?
Yeah, so we've actually extended the inner boundary for the test particles to be a dipole field below the inner boundary for the MHD simulation, such that now that they can kind of propagate into that gap region that we didn't have in the MHD solution, so that that can ultimately, and then we extend that down essentially to just above the Earth's surface, so that hopefully the particles that are escaping through that surface are precipitating through the loss cone.
Okay, so you're tracing them all the way through the dipole field.
Yes.
Okay, cool, thanks.
More comments or questions? I don't know if Don, you wanted to add anything on the question on SAPs.
Sure, yeah, thanks for the chance. And also thank you to Jeff for that question. So yeah, we haven't really looked into the particle tracing yet, but just as you have seen the presentation, we did have conducted some test particle simulation, trying to understand the processes. So probably we should talk more after this talk, and we are open to all kinds of collaborations, definitely.
Great, thank you.
Thank you.
Anthony?
Yeah, hi guys. Yeah, this is a question for Adam. Nice results, Adam. Could you say a little bit more about that plot that showed the wave particle, the precipitation, that polar plot that showed the precipitation?
Yeah, so that was work led by Kevin Pham, where he took basically output from our test particle simulations at the inner boundary and basically mapped them down, dipole mapped them down to the ionosphere and calculated the energy spectrum and energy flux that are precipitating just from only the test particles that essentially precipitated over a 3-hour period in our simulation. And here you're seeing, I think he's done it by co-latitude, but this essentially has waves at all MLT ranges and L shell ranges. So this is, yeah, so that's how we create those precipitation maps. And ultimately we can basically calculate these precipitation maps at all energies of the radiation belts specifically and produce these maps.
Yeah, no, there's a lot of flexibility. So that you answered one of my questions, I think, that it's over a 3-hour period, and is that during the main phase or early?
Yeah, this was, yes. Sorry, no, this was during the recovery phase of the storm, just for this one event. But we have are starting to look at the main phase during this storm in particular, where pose measurements did see coarse wave activity. So in the future, we'll kind of update that, update these precipitation maps when we have more information going forward.
Yeah, right. Yeah, thanks a lot. Nice.
I'll just add, if I might, to what Adam said, which is the nice thing about this precipitation map is that, as I described in the beginning, we have a fully coupled model of ionosphere, thermosphere, and magnetosphere, and going forward, we will actually be coupling to WACMX, which goes all the way to the ground, essentially. So we will be able to, with this modeling capability, to look at the effects of these high energy, of this precipitating high energy particles in the atmosphere.
Adam, there is another question in the chat that Kareem already took a crack at. If you'd like to look at it and comment if you would like anything in addition to what Kareem put in.
Yeah. So Kareem's absolutely correct. We basically the diffusion coefficient.
Yeah. Why don't we repeat the question?
Oh, sorry. Yes, absolutely. Yeah. So the question was the electron scattering effect strongly depends on the electron density and the wave model, which can influence which electron energies can actually resonate. So the question is it feasible to incorporate both the event-based observed wave parameters and a statistical wave model? Just to expand on what Kareem has said, that we do use the density, the dynamically evolving density in plasmasphere in our MHD simulation, as well as the magnetic fields. Currently we assume that the wave model, the wave spectrum is Gaussian, but it is easy to kind of update our diffusion coefficient to incorporate the actual wave spectrum if we have that information. And additionally, we're using kind of a statistical empirical wave model here, but again, it's just, as Shanshan showed, it's just we can easily transition that to be kind of event-specific waves as well, if we have them for any given event. So that in theory are, the way we're calculating these wave particle interactions, they're driven almost entirely by the upwind solar wind conditions, as well as the wave conditions applied from the wave model themselves.
Excellent. And we're right on top of the hour. Do we have any last minute comments or questions? If not, I would like to thank the speakers again, and a quick reminder for those who joined us a bit late is that we're taking a summer break for 3 months, and we will resume the series in September. We have great ideas for new topics that we will bring you in this format of multiple speakers followed up by discussion. So please stay tuned to SPA announcement and of course to the RBSP email list. Thank you all and have a great summer.